Oh, all right. So let me just explain a bit about the. Oh, sorry, you have to make me host. Okay. So. All right. So I have this alpha wedge d alpha power n minus 1. This is a nowhere zero this is a nowhere zero top degree form on the unit tangent bundle. Actually, what I want to say that this is equal to a constant times the volume form, Riemannian volume form, of T1M with the Sasaki metric. So, I mean, T1M is a submanifold of Tm. So the Sasaki metric restricts to a metric on T1M, right? So you can think of T1M as a Riemannian manifold with the induced metric from the Sasaki metric, okay? So I want to say that the volume form of this is nothing but this alpha wedge d alpha power n minus 1. Okay, so so that's just a simple calculation, because what I do is I take a point theta equal to PV in T1M, and I take what I have to show that this applied to any orthonormal basis of the tangent space to T theta T1M, this is a constant, right? Then it will be up to a constant, it will be the Riemannian volume form, right? The Riemannian volume form is characterized by the fact that applied to any orthonormal basis of the tangent space of T1M, it gives 1, right? Yes? Okay.
Yes, sir.
So how do I get an orthonormal basis? So I take g theta. So this is v comma 0. So norm g theta is norm v, which is 1, okay, because we're in T1M. And then now I take W1 to Wn minus 1. I take this to be an orthonormal basis of V perp, okay, which is a subspace of TPM. All right. And then I let xi I be the vector with horizontal component Wi and vertical component 0. Okay. So so these are in H theta, which is a subspace of T theta T1M, right? Okay. I goes from 1 to n minus 1. And then I take, so note that norm xi I is equal to norm Wi equal to 1. And then I take eta I to be j of xi I, j theta of xi I. So this will be the vector 0 comma Wi, right? So this also belongs to T theta T1M, right? Because K theta of this is Wi, and Wi inner product with V is 0. So this is in the tangent space to the unit tangent bundle, right? Okay. So I equals 1 to n minus 1, and norm eta I is also norm Wi, which is 1. Okay. So then G theta comma xi 1 eta 1 up to xi 2 eta 2 up to xi n minus 1 eta n minus 1. You can see this is an orthonormal basis of T theta T1M. Is this clear? Yes?
Yes, sir.
And also, what about these vectors xi1 eta 1 and xi2 eta 2 up to xi n minus 1 eta n minus 1? This is an orthonormal basis of the kernel of alpha theta, right? Restricted to T theta T1M. Is this clear?
Yes.
Yeah, okay. These are all the directions where the foot is perpendicular to, the movement of the foot is perpendicular to V. So xi1 to xi n minus 1, these are perpendicular to V by choice, right? The foot is perpendicular to V, Wi's are perpendicular to V. And the eta's are vertical, the movement of the foot is 0. So these are already in this kernel of alpha. Okay, and together they form a basis for the kernel of alpha, right? Because there are 2n minus 2 elements, and the kernel of alpha has dimension 2n minus 2. Okay? Yes? So now what is alpha wedge d alpha power n minus 1 of this basis g theta xi 1 eta 1 up to xi n minus 1 eta n minus 1. So this is alpha is up to a constant. This is alpha wedge omega power n minus 1 of this basis. So let me write this basis as g theta xi 1 j xi 1 up to xi n minus 1 j xi n minus 1. Okay. And notice by construction, so these are all in the kernel of alpha. This xi 1 j xi 1 up to xi n minus 1 j xi n minus 1. These are in the kernel. So when I look at this alpha wedge, this is going to be some other constant c prime times alpha of g theta into omega power n minus 1 of this xi 1 j xi 1 xi n minus 1 j xi n minus 1, right? Yeah, this is the calculation we did when we showed that alpha wedge d alpha power n minus 1 is non-degenerate for a contact form, right? Is non-zero for a contact form. We took an element which was on which alpha was non-zero, and the rest of the basis we took to be a basis of the kernel of alpha, right? And then we saw that this alpha wedge d alpha power n minus 1, it splits on this basis, right? It splits. Yes, remember this? Yes, can you hear me? Yeah, can you hear me?
Yes, sir.
Hello?
Yes.
Yeah, is this okay? So this is all right. This is the calculation we did earlier, right? That when you're doing alt, the permutations that you're allowed have to move g theta to the first spot, right?
Yes, sir. We did this.
We did this computation. But now what is omega power n minus 1 of this? Because of the way we've chosen the xi i's and these j's xi i's, and because omega is defined in terms of the Sasaki inner product and j, this omega is equal to omega restricted to kernel of alpha. This is equal to a sum I goes from 1 to n minus 1 xi I star wedge eta I star, right? Because omega of xi I xi j is equal to 0 is equal to omega of eta I eta j, and omega of xi I eta j is delta ij, right? Yes?
Yes.
This is the same calculation that we did for R2n, right? And using R2n as Cn and J as the multiplication by I. It's the same calculation, right? It's the same calculation.
This is computation. Yeah.
Right? Okay. So then we're done. So this omega power n minus 1 of this will be C factorial into alpha g theta into n minus 1 factorial, right? Because omega power n minus 1 restricted to kernel alpha. I just raise this to the power n minus 1. What I'll get is this will be n minus 1 factorial into xi 1 star wedge eta 1 star wedge dot 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 wedge xi n minus 1 star wedge eta n minus 1 star. Is this clear? Yes?
Yes, sir.
This calculation we also did earlier, right? When I raise this standard symplectic form power and power the dimension or half the dimension, then I'll get that factorial times this wedge product, right? And this applied to this basis will give me 1. So this will just give n minus 1 factorial, and alpha of g theta, this is just 1. So the whole thing gives me some constant C0, which is independent of theta and independent of the orthonormal, independent of the choices of the wi's and so on. So if for one orthonormal basis, the value is a constant, then for any other orthonormal basis, it will be the same, right? Because the change of basis from one orthonormal basis to another, if they're positively oriented, it has determinant +1, right? So, okay. Is this clear? Yes?
Yes.
Okay, so therefore alpha wedge d alpha power n minus 1. This is a constant times C0 times the volume form d vol of T1m. Okay, this is what I wanted to say. All right. So therefore, what we get is finally the geodesic flow restricted to the unit tangent bundle it preserves the Riemannian volume of the unit tangent bundle, right? Okay. Because it preserves alpha, so therefore it's going to preserve alpha wedge. I mean, it's going to preserve d alpha as well, and therefore it will preserve this wedge product. Okay. So phi t star alpha equal to alpha implies phi t star alpha wedge d alpha power n minus 1 equal to alpha wedge d alpha power n minus 1. So implies phi t star of d vol T1n equal to d vol T1n. Okay. So the geodesic flow preserves Riemannian volume on the unit tangent bundle. Is this all right? Yes?
Yes, sir.
Okay, so if M is a compact manifold, then the unit tangent bundle is also compact, right? Yes? Because
Yes,
the fibers are spheres and the base is compact, so the total space is compact, right?
yes, sir.
It's just a compact union of compact spaces of spheres. So it's a compact space. And so then the volume is finite, right? So then it becomes a measure preserving flow of a finite measure space, right? And you can divide by a constant so that it becomes a probability measure. The total volume becomes 1. And so then it becomes yeah. So it becomes a group of transformations preserving a probability measure, right? And so then you can do ergodic theory for the geodesic flow. You have an invariant probability measure, and you can ask, is it ergodic, and so on. So you can investigate the measure theoretic properties of the geodesic flow with respect to, so this measure is called the Liouville measure. Okay, this measure is called the Liouville measure. This is called, so it's just the Riemannian volume measure on the unit tangent bundle. So this is called Liouville measure on T1n. Okay, so we've proved that the geodesic flow preserves the Liouville measure on the unit tangent bundle. Okay. It's also called the Lebesgue measure sometimes. Yeah. Okay, any questions? Any questions? So for those of you who know ergodic theory a little bit, or at least who know the definition of ergodic, there's one natural question, right? What is that question?
But this transformation is ergodic or strong mixing, these sort of questions.
Right, with respect to Liouville measure, right? With respect to Liouville measure. And the answer to both is yes, if the manifold has negative curvature. Then in fact, it is mixing with respect to Liouville measure. But that's a very difficult theorem. It's a very difficult theorem. It's easier to show that it's ergodic. So that's weaker, much weaker than mixing. So yeah, so in fact, it is if the manifold has, if it's a compact manifold of negative curvature in any dimension, then the geodesic flow with Liouville measure is ergodic for the geodesic flow. So that means the only invariant measurable sets for the geodesic flow either have full measure or zero measure, right? Either have full measure or zero measure.
Yes, yes.
Okay, so that means negative curvature. So if there's time at the end of the semester, there's a famous argument of Hopf, the Hopf argument, which proves ergodicity of the geodesic flow. It's a very famous argument, so I might try to just sketch that a bit. If we get there, if we have time by the end of this course. I don't know how much time we'll have, but that's okay. Whatever we do is fine. So, okay.
Yeah, that would be great, sir.
Yeah, I'll try and give the proof of that. It's a famous theorem of, I think Anosov, yeah, Anosov was the first to prove ergodicity of the geodesic flow in negative curvature. Yeah. Hopf proved it for hyperbolic surfaces. So those have constant negative curvature, -1, and it's only dimension 2. But then Anosov saw that his argument, with some very difficult technical issues, could be used for also manifolds of variable negative curvature in any dimension. So there are some technical issues to overcome. So that's what Anosov did. Yeah, that's what Anosov did. Okay. Okay, so all right. Sorry for going over. So let's stop here today. All right. No more questions? Any questions? Okay, so then let's stop here. Okay, so I'll see you next week.